of similar problem, but we can solve easily. Here, you look, we have the dimensions, like this distance is 15, the length 10, this is 20. The pressure and the temperature is given, the velocity is given 7 meters per second. It says disregard the entrance effect, determine the pressure loss in these sections. So we'll calculate the pressure loss. What do you mean by this entrance effects? Disregard the entrance effects. Who can tell me what it means actually? If we disregard the entrance effects, what's the meaning of that? What does it mean? Can anyone tell? You know the entrance effects we discussed during the lecture. So in this question it says disregard these entrance effects. Can anyone tell me what's the meaning of this section, like disregard the entrance effects? That is telling your flow is,
Is it saying to ignore the minor loss?
It's not, we'll not think that way. It is actually telling that your flow is fully developed, because we know it is, like say this is a pipe. What is the entrance region? The point where the flow become fully developed. Until this length, the flow is gradually developing, and all things changing here. So at this point, that means at least 10 to the, if it is D, at 10 times of the distance of the diameter, the flow usually, it becomes fully developed. A flow could be turbulent over there. So when it says this region up to this, from here to here, this is called the entrance region, and this length called the entry length. So when it says you just disregard this, that means now you have only this section. That means your flow is fully developed. You know what I mean? So that's actually, we need to use the assumptions that the flow is fully developed, and we'll solve this question that way. So the assumptions for this problem, we'll say this is a steady and incompressible. We'll say it is fully developed flow. Okay, this is fully developed flow. So the given informations here, we know the length is 10 meters and the pressure is 1 atmospheric pressure and the temperature is 35 degrees centigrade. So the question is, we need to calculate the pressure loss. The pressure loss means delta P, and it is equal F L over D V square over rho V square over 2. This is the pressure loss formula, rho V square over 2. So that means we need the friction factor, and friction factor means we need epsilon over D, epsilon over, we need the Reynolds number, and we need, to get the Reynolds number, we need the diameter. You look here, guys, just try to understand. This is same thing from here, what we did earlier. This formula is a little bit different. The difference between head loss and the pressure loss I showed you earlier. But the only issue is, when it is delta P, still we need the D. What is D? Diameter. But we have, it is a rectangle. So we know diameter is for circle, but it is rectangle. So we need to use the hydraulic diameter here. So that means initially we will calculate the hydraulic diameters. So the first part is, let's calculate hydraulic diameter, then Reynolds number, then epsilon over D, then F, then delta P. Okay, and if we need the value, okay, I think that's all we need. So here, let's start with the solution. So hydraulic diameter. Hydraulic diameter D has, for rectangle, the formula is, the 4AC over P, the perimeter. Area is, if it is the rectangle, so the area we can easily say, okay, this distance and this distance. So if I say this is A, this is B, so let's say this is 4AB, and the perimeter means we need to consider this whole distance, like, so this is A, this is A, this is B, this is B. So it will be 2 into A plus B. This is actually the formula for rectangle. You look here, this is, if I say this is A, this also A. If it is B, this is also B. So now substitute all the value. This is 4. A equal 15 centimeter, that means 0.15. And 20 centimeter, that means 0.2. 2 into 0.15 plus 0.2. So it will be the hydraulic diameter 0.1743 meter. So this is the hydraulic diameter for this problem. So this diameter we're going to use when we will calculate the Reynolds number, when we will calculate the pressure loss. So this is the hydraulic diameters. Now just calculate the Reynolds number. So the Reynolds number here, rho, B, D, and mu. So you look here, we don't know this viscosity and this density. But what we know from this problem is the temperature is 35 degrees centigrade and atmospheric pressure. So for that conditions from the table, we will get the density is, this is density of air, it's not water. So the density for air, it is 1.145. The velocity we have in this question is given 7 meters per second. The diameter we got to 0.17143, and the viscosity is 1.895 and 10 to the power minus 5. Hey, look, if you ask me how you got this value and this value, the answer is it's from the table. Like the air properties at different temperature. This is for 35, and it is week 10. So I believe that I don't need to show you again, right? Like how to get these two values from the table. So the Reynolds number, guys, we'll see it will be 72,506. It is greater than 2,300, so the flow is turbulent. In some books or in the solution, you see it's written like it's greater than 4,000. It doesn't matter. For internal flow, if it is greater than 2,300, you will see it is turbulent, okay? But 23 to 4,000, we usually see this is the transition. And transition means actually that's the phase change. So it's not anymore laminar. So transitional, or, so you can say I showed, like when I told you that the guy did this research earlier during my master's. So I found the flow becomes like this. Initially the flow profile is, let's say, like this. Then we got like a periodic profile like this. So it's follow this periodic profile, and then it becomes like this. So this flow profile, it becomes like this. So this is, we can say this part, it is laminar. This is transient flow. This is turbulent. So the combination of these two, this is actually the new phase. This part only laminar. So there is no charge for transients, but we usually say transient is, this is turbulent. Okay. Yeah. So we got the flow is turbulent. Now epsilon over D. When we have the Reynolds number, then epsilon over D. Especially the relative roughness for this problem, it is, we are using actually a commercial steel. So for commercial steel, the roughness from the table I showed you earlier, it is 4.5 and 10 to the power minus 5 meter. So our diameter is 0.1743 meter. So 0.1743 meter. So this epsilon over D value, it will be 2.625 and 10 to the power minus 4. So this is epsilon over D. For this problem, we will actually use the Colebrook equations. So the Colebrook equations is, we know 1 over square root of f negative 2 log epsilon over d over 3.7 plus 2.5 1 over Reynolds number into f. So this is the Colebrook equation. So what we will do, guys, we already know the Reynolds number. This is 72,000 something, and we know this is epsilon over d values. So we are going to substitute this two value here, and then we'll get f. So if I just write it down in the next phase, then it will be 1 square root of f negative 2 log 2.625 and 10 to the power minus 4 3.7 plus 2.5 on, and the Reynolds number is 72,506 square root of f this. So the f will get 0.02036. So this is actually from the equation solver. Okay, you can, if you want, you can just try it later on maybe. And now the delta P, the pressure loss, it will be F L over D rho V square and 2. So you just substitute these values here. The density, the friction factor is 0.02036. Length is 10 meter, diameter is 0.17143. And the density is 1.143, velocity is 7 square over 2. So we need to convert the units. So 1 Newton equal 1 kg meter per second square. And if I can convert it into Pascal, so it is 1 Pascal equal 1 Newton per meter square. And we'll get it is 33.317 plus delta P. This is actually the solution of this problem.